What if I told you the race to build a quantum computer has already been won? Not by a company building the quantum computer itself, but by the one building the cage around it. It sounds impossible, but stick with me. The company is one you definitely know, but the strategy is one of the most brilliant and stealthy in modern technological history. Hello, and welcome to Mindcast. I'm your host, Will. Today, we're pulling back the curtain on a topic that sounds like pure science fiction, but is happening right now: the quantum computing revolution. But we're not just talking about the mind-bending physics of qubits and superposition. We're talking about business strategy, market domination, and how NVIDIA, the undisputed king of AI hardware, is executing a quiet, systematic plan to control the next great technological leap before it even takes off. The global computing infrastructure is undergoing a tectonic architectural shift, transitioning from the era of classical general-purpose processing to an epoch defined by accelerated, highly parallel computational fabrics. As artificial intelligence fundamentally reshapes the modern data center, a parallel yet intimately connected revolution is occurring within the domain of quantum computing. This is where our story begins. To understand this strategy, let's rewind to NVIDIA's 2025 GPU Technology Conference. CEO Jensen Huang hosted what was billed as a Quantum Day fireside chat. But this wasn't just a panel, it was a summit, a flex of strategic muscle. On stage with him were the leaders of almost every major quantum hardware company on the planet: D-Wave, IonQ, Quera, Rigetti, Quantinuum, and many more. These are fierce competitors, each pioneering different, radical approaches to building a quantum computer: superconducting circuits, neutral atoms, trapped ions. They are locked in a brutal, capital-intensive war for physical supremacy. Yet, they were all there, united on NVIDIA's stage. Over the next 20 minutes, we're going to deconstruct this strategy piece by piece. By the end of this episode, you'll understand the brilliant, multi-billion-dollar playbook that NVIDIA is executing, and you'll see why the future of quantum computing is fundamentally and perhaps permanently tied to the AI infrastructure we have today. The gathering was a testament to NVIDIA's central position in the burgeoning quantum ecosystem. It featured not just the big names, but a comprehensive lineup of innovators from companies like Atom Computing, Inflection, Microsoft, and PsiQuantum, showcasing the breadth of NVIDIA's partnerships and influence. The gathering featured pioneers such as Alan Baratz of D-Wave, Peter Chapman of IonQ, and Mikhail Lukin of Quera Computing. These weren't just figureheads. These are the leaders building the very quantum processors that are supposed to compete with each other. During the talks, visionaries like Mikhail Lukin laid out the benchmarks for real-world utility, challenging the field to deliver 10 new, distinct scientific discoveries using quantum processors in the near future. This event wasn't just a friendly chat about the future. It functioned as the formal integration of the entire fragmented quantum industry into NVIDIA's cohesive hardware and software ecosystem. It was a declaration that while NVIDIA had no intention of building a quantum computer itself, it was dedicating itself to creating the indispensable underlying architecture for everyone else. Jensen Huang explicitly likened this effort to the creation of the CUDA ecosystem that now dominates classical AI, and by 2026, this declared intent materialized into concrete, state-of-the-art technological deployments. NVIDIA systematically released a suite of advanced toolchains: the open-source CUDA-Q platform, the NVQ-Link hardware interconnect, and the NVIDIA Ising family of AI models, all designed to blend emerging quantum technologies with established classical computing. He was telling the world the game is not to build the best quantum computer, but to build the platform that all quantum computers must depend on. This brings us to the core of NVIDIA's strategy, the principle of commoditizing the complement. Now, that sounds like a dry business school term, but it's the absolute key to this entire story. The simplest way to understand it is the classic gold rush analogy. During the California gold rush, the people who made the most reliable and lasting fortunes weren't the individual prospectors digging for gold, most of whom went bust. It was the entrepreneurs who sold the picks, shovels, and blue jeans to all the prospectors. They didn't care who found gold, they just needed people to keep digging, and they sold the indispensable tools to do so. In this analogy, NVIDIA's GPUs are the picks and shovels, and they have already perfected this playbook in the AI industry to defend their turf. Just a few years ago, NVIDIA faced a structural, existential threat. The biggest buyers of their chips, the hyperscale cloud providers like Google, Amazon, and Microsoft, started designing their own custom AI silicon. Google has its tensor processing units, or TPUs, capturing workloads from major players like Apple. AWS has its Trainium and Inferentia chips. If the artificial intelligence market became dominated by closed-source models heavily optimized for these proprietary chips, the end user would be completely agnostic to the hardware layer. The hyperscaler would capture the entire margin, and NVIDIA would be systematically excised from the value chain. So, how did NVIDIA counteract this disintermediation? They aggressively commoditized the complement. The complement to their hardware is software, the AI models themselves. Filings and industry reports indicate NVIDIA committed an astonishing $26 billion to build and support open-weight artificial intelligence models. This wasn't just a donation, it was a multi-pronged venture capital and infrastructure blitz. Why? Because these open-source models were all built and optimized to run on NVIDIA's own proprietary software platform, CUDA. By making the software free, they made their hardware indispensable. They created a world where if you wanted to use the best, most accessible AI, you had no choice but to buy NVIDIA's picks and shovels. It was a defensive masterstroke, and now they're running the exact same play in the quantum realm. For example, they poured money into Mistral AI, a Paris-based open-source leader participating in a €1.7 billion funding round. They heavily backed Reflection AI, a startup developing open-source models for the US and its allies. Beyond commercial startups, they granted a combined $152 million to the Allen Institute for AI to support public sector open science. This massive subsidization ensured that the highest quality, most advanced AI software remained freely available and not exclusively tethered to any single proprietary cloud. But this strategy wasn't just defensive, it had a massive offensive component, expanding the total addressable market through sovereign AI. While defending its existing hyperscaler market was crucial, NVIDIA recognized that to achieve a projected multi-trillion-dollar global AI factory build-out by 2030, it had to unlock the market outside the major cloud providers. So, how exactly are they applying this playbook to the quantum world? It comes down to a three-layer toolkit they're giving away to the entire industry. Think of it as the ultimate quantum starter pack. The most structured manifestation of this strategy was the NVIDIA Nematron Coalition, announced at the 2026 GTC. This coalition pooled GPU allocations across member institutions, enabling them to achieve frontier-scale training without any single institution needing to fund astronomical compute costs. It featured specialized members like Mistral AI for core models, Black Forest Labs for visual intelligence, and LangChain for the execution layer, all working together to create state-of-the-art open models that could challenge the closed system monopolies. The first piece of the toolkit is the software foundation, a platform called CUDA-Q. The foundational layer of NVIDIA's quantum strategy is the CUDA-Q software platform. As the industry transitions from the noisy intermediate-scale quantum era toward large-scale fault tolerance, the complexity of managing algorithms that interleave massive classical data processing with delicate quantum logic has become a primary developmental bottleneck. Historically, quantum programming involved a fragmented, highly inefficient workflow. CUDA-Q dismantles this paradigm. It is an open-source, QPU-agnostic quantum development platform designed explicitly to orchestrate the heterogeneous hardware and software required for utility-scale applications. The second piece of the toolkit is the hardware interconnect called NVQ-Link. While CUDA-Q provides the high-level software abstraction, the physical realities of quantum physics demand highly specialized hardware. The greatest existential threat to quantum computing is decoherence, the rapid, inevitable degradation of quantum states due to microscopic environmental noise, thermal fluctuations, and control imperfections. To achieve fault tolerance, quantum systems must actively perform quantum error correction, or QEC. By extending standard classical programming languages like C++ and Python with specialized quantum kernels, CUDA-Q allows developers to write a single unified hybrid application. Under the hood, it uses a high-performance quantum compiler, NVQ++, which is based on the industry-standard LLVM toolchain, ensuring profound interoperability with all leading models and tools for accelerated computing. The strategic brilliance of CUDA-Q lies in its aggressive hardware agnosticism. NVIDIA claims the platform integrates with approximately 75% of all publicly available QPUs, seamlessly bridging the gap between vastly different qubit modalities. This capability has driven rapid adoption, with companies like Pascal and Quantum Circuits integrating it into their workflows. As Loïc Henriette, CEO of Pascal, noted, this integration provides developers with a unified programming model that drives real-world impact and faster innovation, effectively transforming quantum processors into native accelerators within a familiar classical computing environment. NVIDIA is building the operating system for the quantum age before the hardware is even fully mature. The mechanics of QEC require a continuous real-time hybrid feedback loop. The system must measure auxiliary qubits to get syndrome data, transmit that data out of the cryogenic environment to a classical computer, execute complex decoding algorithms to identify the error, and transmit a correction pulse back to the QPU, all before the logical qubit state collapses. This entire decoding window frequently spans merely a few microseconds. Traditional cloud and data center networking, which incurs latencies in the high microseconds or milliseconds, is fundamentally useless for this task. It is a physics-bound hardware bottleneck. A critical part of this operating system strategy is solving a fundamental bottleneck in quantum development: validation. Before nascent quantum algorithms can be run on expensive, error-prone QPUs, they have to be rigorously simulated on classical computers. But this simulation is notoriously resource-intensive, with memory needs scaling exponentially. CUDA-Q addresses this head-on by leveraging NVIDIA's powerful Q-quantum simulation engine. This has a profound commercial impact. For example, PsiQuantum, a company building a utility-scale photonic quantum computer, integrated CUDA-Q into its software suite and saw a staggering 450 times performance acceleration compared to traditional CPU-based simulations. This isn't just an efficiency gain, it's a critical enabler for the entire industry, allowing developers to validate complex algorithms at scales that were previously impossible.
And that brings us to the third and most ingenious part of the toolkit, the NVIDIA Ising Open Model family. While NVIDIA Q-Link provisions the physical bandwidth, the actual mathematical process of decoding quantum errors and calibrating thousands of noisy qubits is a computationally monumental task. Traditional algorithmic approaches like graph-based matching are rapidly failing to scale with the increasing qubit counts and error complexities of modern processors. To solve this, NVIDIA engineered NVQ-Link. It is an open platform architecture designed to physically and logically integrate quantum hardware with accelerated computing.
Operating as a high-speed, microsecond latency interconnect, NVQ-Link connects the quantum controllers directly to NVIDIA GPUs using technologies like RDMA over Ethernet to completely bypass the slow, traditional CPU host. It's not just a software link, it's a physical necessity. Through this, NVIDIA is declaring that the QPU is not a standalone machine. Rather, it is an ultra-specialized accelerator that must be permanently housed within an NVIDIA-architected data center environment. To overcome these severe limitations, NVIDIA applied its core competency, artificial intelligence. They turned the problem of quantum error correction into a massive, continuous, single-user inference task. The Ising family represents the world's first open-source AI models explicitly designed to combat qubit noise at scale. By releasing these models with a permissive license, NVIDIA encourages global researchers to fine-tune them, preserving data sovereignty for secretive QPU builders while ensuring NVIDIA's AI frameworks become irreversibly embedded into the operational heart of quantum laboratories. The software that drives this is called CUDA-Q Real-Time, which supports multiple execution modes to balance latency and flexibility. The default 3-kernel dispatch uses cooperative kernels for receiving, processing, and transmitting data, while a unified kernel mode offers the absolute lowest latency by consolidating all phases into a single persistent kernel. This level of sophisticated engineering demonstrates a deep understanding of the physics involved. And where do these essential AI models run? You guessed it, on NVIDIA GPUs. By making this critical AI component open source, they've transformed the problem of quantum error correction into a massive, continuous AI inference task, a task that fuels endless demand for their core hardware product. The architectural shift is profound. Instead of routing every syndrome measurement to a slow global decoder, a high-throughput GPU-accelerated three-dimensional convolutional neural network acts as a pre-decoder. It performs a rapid approximate first pass, resolving the vast majority of localized errors in real time. Only the most complex, unresolved residual cases are forwarded to the global decoder. The performance improvements are transformative. For example, the Ising Fast model, with roughly 912,000 parameters, achieves a 2.5x reduction in decoding time and a 1.1x improvement in the logical error rate. NVIDIA projects that using FP8 precision on GB300 GPUs, this model could achieve a latency of just 0.11 microseconds per round. The larger Ising Accurate model, with 1.79 million parameters, is slightly slower but yields a vastly superior 1.53x improvement in the logical error rate. But NVIDIA's use of AI in quantum doesn't stop at error correction. It extends to completely automating the painstaking process of calibration. Qubits are inherently delicate. Their resonant frequencies drift. Control pulses degrade, and thermal fluctuations constantly alter their operational baselines. Traditionally, managing this involves highly trained physicists manually executing experiments and analyzing visual scatterplots, a process that is overwhelmingly slow and entirely unscalable. This brings us to the final and perhaps most crucial piece of the puzzle, the broader implications. The grand plan. When you put these three layers together, the universal software, the essential physical link, and the AI control brain, you realize this is about total ecosystem capture. It's not just about technology, it's about owning the entire research and development pipeline for the next generation of computing. This brings us to the geopolitical and institutional dimensions of this strategy. To secure its position at the absolute center of the geopolitical race for quantum supremacy, NVIDIA must firmly capture the academic and institutional research sectors that drive foundational discovery. Mirroring its strategy of subsidizing academic open science in AI, NVIDIA announced the establishment of the NVIDIA Accelerated Quantum Research Center, or NVAQC, in Boston.
This move effectively guarantees that the next decade of foundational quantum breakthroughs, novel error correction codes, revolutionary calibration protocols, deep material science discoveries are natively conceptualized, built, and ruthlessly optimized on the CUDA architecture. This institutional capture neutralizes the risk of a competing, non-NVIDIA architectural paradigm taking root within the academic environments that generate the industry's future engineering talent. They are ensuring the next generation of quantum experts thinks, dreams, and codes in CUDA.
Strategically positioned to leverage the immense world-class talent pools of both Harvard University and MIT, this lab is designed to be the most advanced hybrid quantum computing research facility globally. Its mission is to solve the industry's most challenging problems, from mitigating qubit noise to transforming experimental processors into deployable devices. By providing top-tier researchers with unfettered, subsidized access to state-of-the-art GPU clusters integrated directly with physical QPUs via NVQLink, NVIDIA is making a powerful statement.
And this leads to the most powerful concluding idea. Many people think quantum computing will replace classical computing. NVIDIA's strategy reveals the opposite is true. The quantum computer won't be a standalone brain. It will be an ultra-specialized coprocessor, completely subservient to a classical AI supercomputer that controls it, calibrates it, and corrects its errors. The arrival of useful quantum computing won't diminish the need for classical computers. It will drive an exponential, insatiable explosion in demand for the highly specialized AI infrastructure that NVIDIA singularly commands. The quantum revolution will be powered by a global build-out of classical AI factories.
So, after all that, what are the big takeaways? I think it boils down to 3 key points. First, the picks and shovel strategy is king. The smartest play in a technology gold rush isn't always to dig for gold, but to sell the essential tools that everyone needs to dig. Second, the future is hybrid. Quantum and classical computers are not competitors. They are partners in a deep symbiotic relationship. NVIDIA isn't just participating, they are building the indispensable bridge that connects them. And third, the control layer is everything. In the end, ultimate power in a new technology stack lies not just in who builds the processor, but in who builds the software and AI ecosystem that controls it. That's the game NVIDIA is playing, and so far, they are winning. NVIDIA is playing chess while others are playing checkers, architecting a future where all roads in the quantum world lead back to their classical AI hardware. It's a bold, multi-billion-dollar bet on infrastructure over invention. If you found this insightful, be sure to subscribe to Mindcast wherever you get your podcasts. We've put a link to the original source documents in the show notes if you want to dive even deeper. Join us next week as we tackle another big idea shaping our world. Thanks for listening.